So we're going to look at second and higher derivatives, and we've encountered second derivatives before because we use them in higher maths to work out the nature of our stationary points. And we need to be able to get our second and higher derivatives for doing our Maclaurin series, which is based on these derivatives, which is part of our sequences and series unit. So the second derivative of the function of x is the derivative of the first derivative of x. So the notation that we're going to use, we're going to look at each of our three different notations and how we're going to express that. Our second derivative in functional notation is going to be f double dash x, or sometimes they use the number 2 in brackets, so that's f2x. In Leibniz notation, it's d2y by dx squared, and in Lagrange notation, it's f double prime. Our third derivative in functional notation is f triple dash x, or f3x. In Leibniz notation, it's d3y by dx cubed, and in Lagrange notation is f triple prime. Our fourth derivative in functional notation, we start to now use Roman numerals, so it'll be fivx for 4, or the number 4 in brackets, f4x. In Leibniz notation, it's d4y by dx to the power of 4, and in Lagrange notation, it's f quadruple prime. So if we want to consider the nth derivative, it will be fnx for the functional notation. It will be dny by dx to the power of n for Leibniz notation, and it will be f n primes for our Lagrange notation. So we want to find all of the derivatives for the function of x equals 4x cubed plus 3x squared minus 5x plus 1. So we've got ourselves a polynomial here. So we're going to use functional notation. So f dash x is going to equal 12x squared plus 6x, take away 5, and our 1 goes to 0. So you can see that our first derivative is 1 power less than our original function. So if we then go to calculate f double dash x, it's going to become 24x plus 6. Our f triple dash x is going to equal 24, and our f4x is going to go to 0, and if we then worked out f5x, f6x, they would all be 0 as well. So what we're saying is that continued differentiation of a polynomial will always lead to 0. So if you look at the power of your original function, you're going to be able to differentiate and have a value for that number of derivatives. Once you get to one more derivative than that, then that constant term differentiates to 0, and any subsequent derivatives will all be 0. That's for a polynomial. However, that's not the case when we come to differentiating trig functions. So we want So we're going to start off with x. We're going to use Leibniz notation this time. So we know that dy by dx and tan x differentiates to the second of x all squared. And I'm also going to rewrite that with it in brackets as sec x all squared, because we're going to have to use the chain rule to find our second derivative. So our second derivative, d2y by dx squared, is our bracket differentiated, so we're going to have 2 times the second of x, and then second of x differentiates to second of x tangent of x, and now we're going to collect our like terms and simplify this to 2 second of x all squared multiplied by the tangent of x. Now, the question I'm asked for the third derivative of y equals tan x, so that's d3y by dx cubed, and you can see I'm now going to have to use the product rule, so I'm going to have u dash v plus v dash u. So I need to work out what my u is, and that will be the 2 second of x all squared, and I'm going to rewrite that as 2 bracket sec x squared, and my v is going to be tan x. So I've already differentiated sec x all squared when I differentiated my first derivative. The only difference is I've got 2 of these now, so u dash is going to be 4 second of x all squared tangent of x. Is going to be the original function squared, so I know that tan x gave me second of x squared. So now I need to substitute those values in. So u prime was 4 second of x all squared tan x, and v is also tangent of x, and I'm going to add on my v prime, which is second of x all squared, and I'm multiplying that by 2 times the second of x all squared. And now I need to factorize. So you can see that I've got a 2 second of x all squared that's common, so I've got 2 second of x all squared outside my bracket, and I'm multiplying that by 2 tangent of x all squared plus a final second of x all squared. So my d3y by dx cubed for my third derivative equals 2 second of x all squared upon 2 tangent of x all squared plus second of x all squared.